Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine pointing an antenna up at a completely dark, quiet patch of the night sky and catching a literal laser beam. And not just any laser beam, but one fired when the universe was just this chaotic toddler.
Yeah, it's pretty wild to think about.
Right. I mean, we are talking about an undeniable signal that has been traveling toward Earth for over 8 billion years. This thing originated from an era long before our solar system even, coalesced.
Exactly. It's ancient history hitting our receivers right now.
So today we're unpacking a record-breaking natural space laser. It was detected by the MeerKAT radio telescope in South Africa, and we're going to look at the mechanical, the quantum, and the astrophysical realities of how you even capture a signal from the deep past.
And we'll get into what a hydroxyl megamaser actually is too, because that's a huge part of the puzzle.
Yeah. Yes, definitely. And ultimately, we want to figure out what the violent collision of two ancient galaxies reveals about the structural evolution of the cosmos. So, for anyone listening who has ever felt totally overwhelmed by the sheer scale of the universe, you're about to get a front row seat to an ultimate cosmic time machine.
It really is a time machine. I mean, the detection of this specific signal fundamentally alters our timeline for observational astronomy.
How so?
Well, we're looking at a system situated at a redshift of roughly z=1.
Okay, let's unpack that for a second.
Sure. So at that distance, we aren't just observing a distant object. We're observing the universe when it was less than half its current age.
Which is just a mind-boggling scale of time.
It really is. And the fact that we can capture the specific quantum signature of a molecule from that epoch and do so in a fraction of the time previously thought possible, it proves that our transition into this new era of wide-field radio astronomy is already yielding structural insights into the cosmic dawn.
Let's start right there, actually, at the concept of redshift and looking back in time. Because, for anyone who follows astrophysics, the basic idea that light has a speed limit is pretty well understood.
Right. Well, it takes time to travel.
Yeah. So we know that looking across space is looking back in time. It's like a letter in the mail. If a friend overseas sends you a letter, the news is old by the time you actually read it.
That's a great analogy, yeah. In space, the light is the letter.
Exactly. But what I want to dig into is the physical reality of what an 8 billion year transit does to that letter. Because when a galaxy at z=1 fires off a burst of radio waves, that wave has to travel through a universe that is actively expanding, right?
Yes, the space itself is expanding.
So by the time it hits the MeerKAT telescope, we aren't just dealing with a faint signal, we were dealing with a stretched one.
That is the crucial mechanical difference between local astronomy and cosmological astronomy. It's called cosmological redshift. The expansion of the universe is a metric expansion of space itself. So as the radio photons emitted by this ancient galaxy travel toward Earth, the physical space they're traveling through stretches.
And so the photon gets stretched with it.
Exactly. Consequently, the actual physical wavelength of the photon is stretched out, which lowers its frequency.
Okay, so if a molecule in that distant galaxy emits a radio wave at a specific resting frequency, say like 1665 megahertz.
It absolutely does not arrive at Earth at 1665 megahertz.
It says the stretching.
Right. Because it has traveled for 8 billion years, the expansion of the universe has stretched that wave down to around half of its original frequency.
Wow. So the engineers and astronomers running MeerKAT, they had to tune their receivers to a completely different frequency band than they would use if they were looking for that exact same molecule in our own Milky Way.
Yes, they did. They had to mathematically predict how much the universe had expanded over those 8 billion years, calculate the resulting frequency drop, and literally just listen there.
That's just an insane level of precision.
It's incredible. And this tells us something profound about the environment we are observing, too.
Like what?
Well, when we look at a galaxy at a redshift of 1, we are looking at an era often referred to as the tail end of cosmic noon.
Cosmic noon. I love that term.
It's a great descriptor. See, in the local universe, the one immediately around us today, galaxies are relatively quiet.
Like our Milky Way.
Exactly. The Milky Way forms a few solar masses worth of stars per year. The gas fractions are lower. The metallicity, which is the amount of elements heavier than helium, is higher.
Right, because generations of stars have already lived and died and seeded the galaxy with heavy elements.
Spot on. And major galaxy mergers are relatively infrequent now.
Yeah.
But at z=1, the universe was structurally different.
It was that chaotic toddler phase.
Yeah, the gas fractions in galaxies were significantly higher. They were churning out stars at incredible rates. And massive violent mergers between galaxies were a dominant driver of cosmic evolution.
Which perfectly sets the stage for the specific signal they found. So they detected a hydroxyl megamaser.
They did.
Now wait, when I hear the word laser, or maser, the visual is usually a highly collimated beam, like a sci-fi blaster or a synthetic optical cavity with mirrors on either end bouncing photons back and forth to build up intensity.
Right, that's the artificial way we build them on Earth.
But a galaxy isn't a manufactured machine, so how does a massive uncontained cloud of hydroxyl gas maintain the population inversion needed for a laser, without the photons just scattering in random directions?
It's a really good question. It requires a highly specific set of environmental conditions that only exist in these extreme environments.
Okay, lay it on me.
To understand the mechanism, we really have to look at the quantum mechanics of the hydroxyl radical, which is just one oxygen atom bonded to one hydrogen atom.
Okay, got it.
In its ground state, the hydroxyl molecule has 4 very close energy levels. We call this hyperfine structure.
Hyperfine structure.
Yeah. These energy levels are determined by the interaction between the magnetic field of the molecule's rotation and the spin of its unpaired electron and the hydrogen nucleus.
So it's like this incredibly delicate magnetic balancing act inside the molecule.
Exactly. And when the molecule drops from a higher hyperfine state to a lower one, it emits a microwave photon at a very specific frequency.
And those are the 1665 and 1667 megahertz frequencies you mentioned earlier.
Those are the most prominent ones, yes.
But just having the gas there isn't enough to create a maser, right?
Mm-hmm.
Because under normal thermal conditions, wouldn't most of the molecules just sit in the lowest possible energy state?
Right, they'd just be lazy. You need something to push them up. You need a pumping mechanism.
A pump. Okay. What acts as a pump in outer space?
In the case of a hydroxyl megamaser, the pump is usually far infrared radiation.
Infrared, so heat.
Basically, yeah. In a violently merging galaxy, you have colossal bursts of star formation and often an actively feeding supermassive black hole, an active galactic nucleus, or AGN.
Right, because everything is crashing together and igniting.
Exactly. And these intense energy sources heat up the massive clouds of surrounding dust. That warm dust then radiates profusely in the far infrared.
Okay, so the dust is glowing with infrared light.
And the hydroxyl molecules absorb those specific infrared photons, which excites them into higher rotational energy states.
They soak up the heat.
Yeah, but they don't stay there. As they quickly decay back down, they don't just return to a random distribution. The quantum mechanics of the decay preferentially populate the upper states of that ground-level hyperfine structure.
Oh, I see. So it artificially loads up the higher energy levels.
Yes, this creates the population inversion. You now have more molecules in the high energy state than the low energy state.
So the trap is set. You've got this entire molecular cloud just sitting there, artificially elevated, waiting for a trigger.
Yes, and the trigger is a single photon passing through the gas at exactly the right frequency.
Just one photon.
Just one to start the avalanche. When that initial photon interacts with an excited hydroxyl molecule, it stimulates the molecule to drop to the lower energy state.
And then it releases its own photon.
Right, but releasing a second photon that is perfectly in phase, moving in the exact same direction, but the exact same frequency as the first one.
Ah, so 1 becomes 2.
2 become 4, 4 become 8. It is an exponential cascade of stimulated emission.
That is so cool. But wait, I want to address the mirror question. How does it become a directional beam that we can actually detect from 8 billion light years away?
Right, without the mirrors.
Yeah, without mirrors to bounce the light back and forth, doesn't the amplification just kind of happen in every direction equally, like a light bulb?
You'd think so, but it comes down to the geometry and velocity of the gas clouds. While there are no physical mirrors, amplification only happens along paths where the gas is velocity coherent.
Velocity coherent, meaning it's all moving at the same speed.
Essentially, if the gas is swirling chaotically, the Doppler shift from the relative motion of the molecules will change the frequency of the photons from the perspective of the molecules themselves.
Oh, right. The pitch shifts like an ambulance siren.
Exactly. And that shift breaks the resonance and stops the cascade dead in its tracks.
So it can't amplify if the gas is turbulent.
Right. However, if you look at a massive disk of gas edge-on, or if there's a long linear filament of gas moving at a uniform velocity relative to the line of sight.
Then the photons can travel immense distances through the cloud without being Doppler shifted out of resonance.
You got it. So the maser beam naturally collimates along the paths of greatest velocity coherence. It's essentially beaming its signal along very specific geometric sightlines.
And we just happen to be sitting exactly on one of those sightlines. That is incredible cosmic luck.
It is. But keep in mind, the scale of this emission is what justifies the mega prefix in megamaser.
Right, because standard masers exist in our own Milky Way, don't they? Usually around individual forming stars?
They do. But a megamaser is millions of times more luminous than those local ones.
So this isn't just one star forming.
No, this is the collective scream of an entire galaxy undergoing a catastrophic transformation. The energy required to pump a cloud of hydroxyl gas to the point where it becomes a megamaser is staggering.
It must take a galaxy-ending event.
It requires the systemic disruption of the entire galaxy. This is why hydroxyl megamasers are almost exclusively found in ultraluminous infrared galaxies, or ULRGs.
ULRGs. Astronomers and their acronyms, I swear.
Hey, it's efficient. But ULRGs are overwhelmingly the result of major galaxy mergers. The detection of this hydroxyl signature is an unequivocal indicator that we are looking at a site of massive cosmic trauma.
Which brings us to the operational reality of how this was actually detected. The signal was caught by the MeerKAT telescope in South Africa in just 5 hours of observing time.
Which is astonishingly fast.
I am really stuck on that 5-hour time frame. Even with massive bandwidth and the inherent brightness of a megamaser, gathering enough photons from 8 billion light years away in a single afternoon seems physically impossible.
Certainly challenges our traditional expectations.
Right, because the inverse square law dictates that as the signal travels, its energy is distributed over an ever-expanding sphere. By the time it reaches Earth, the flux density should be buried so deep in the thermal noise floor that a 5-hour integration shouldn't even register a blip.
That's the math, yeah.
So what is MeerKAT doing differently that breaks that expectation? How is it drinking from a fire hose of cosmic noise and actually finding something?
Well, MeerKAT is a marvel of modern radio interferometry.
Yeah.
And to really understand its efficiency, we need to look at both its physical architecture and its computational backend.
Okay, let's start with the physical.
MeerKAT is not a single giant dish. It is an array of 64 individual antennas, each 13.5 meters across, spread out over distances of up to 8 kilometers.
Oh, wow, 8 kilometers.
Yeah. And by linking these antennas together, astronomers use a technique called aperture synthesis to create a virtual telescope that has the resolving power of a single dish 8 kilometers wide.
Right, because in radio astronomy, the resolution is dictated by the maximum distance between your antennas, which are called the baselines.
Thanks, that.
But resolving power just gives you a sharper image, right? It doesn't inherently give you the raw sensitivity to pull a hyper-faint signal out of the noise in 5 hours.
You're right. Sensitivity is a function of the total collecting area, the system temperature of the receivers, and the bandwidth. And this is where MeerKAT absolutely excels.
Okay, break that down for me.
Well, first, the receivers on these antennas are cryogenically cooled.
Like sub-zero cool.
Very sub-zero. This is done to reduce the internal thermal noise, literally the random jitter of electrons in the electronics, to an absolute minimum.
Got it. So the equipment itself is whisper quiet.
Right. But the real leap forward is the correlator and the bandwidth. MeerKAT can digitize and process an enormous swath of the radio spectrum simultaneously.
I really want to focus on the data processing side of this because capturing the data is only half the battle.
It's arguably the easier half, honestly.
Right. If MeerKAT has a massive bandwidth and is incredibly sensitive, it means it is picking up everything.
Everything.
It's capturing the ancient hydroxyl megamaser, sure, but it's also capturing the microwave background, the synchrotron radiation from our own galaxy, and critically, all the terrestrial radio frequency interference, the RFI.
Bane of radio astronomers everywhere.
Seriously, we are talking about satellite communications, GPS, cell towers, airplane radar. How do you isolate an 8-billion-year-old wind spur when you are sitting in the middle of a planetary-scale rock concert?
That is the defining challenge of modern radio astronomy. And the raw data rate from the MeerKAT correlator is on the order of terabytes.
Terabytes, just constantly flowing in.
Constantly. To process this, the data is sent to the Inter-University Institute for Data-Intensive Astronomy, or IDA, where high-performance computing clusters run complex calibration pipelines.
So if we use like noise-canceling headphones as a model, is the algorithm basically generating an inverse wave of the terrestrial noise, the satellites, the cell phones, and subtracting it from the raw feed, leaving only the ancient cosmic whisper?
Well, it's closer to the reality of the software pipeline than a simple filtering analogy, but it's more complex than that.
How so?
The correlator and the subsequent software pipelines have to identify the specific phase and amplitude signatures of terrestrial RFI.
Phase and amplitude.
Yeah. Because terrestrial sources are very nearby, their wavefronts are curved when they hit the array across that 8-kilometer distance and they appear localized.
Ah, okay. Like ripples in a pond radiating from a rock you just threw.
Exactly. Conversely, a plane wave arriving from deep space from 8 billion light years away hits the array with a completely different flat phase signature.
Because it's traveled so far that the curve has essentially flattened out.
Precisely. The algorithms analyze the data in the time-frequency domain, searching for spikes in power that violate the expected fringe patterns of a celestial source.
And then it just flags them.
It flags them or mathematically subtracts that interference. It requires trillions of floating point operations per second just to clean the data before you can even begin to look for the science target. It's like a high-tech car wash for data.
A high-tech car wash running on supercomputers. That's wild. And the wide bandwidth allowed them to do something unprecedented during this observation, right? They didn't just find the redshifted hydroxyl line.
No, they didn't. Because they were capturing such a massive chunk of the spectrum, they simultaneously detected the redshifted neutral hydrogen absorption line.
Simultaneous detection, wow.
Yes, and the simultaneous detection of both the neutral hydrogen, or HI, and the hydroxyl, OH, is a massive observational victory.
Why is it such a big deal?
Well, neutral hydrogen emits and absorbs radio waves at a resting frequency of 1420 megahertz. Hydroxyl, as we discussed, is around 1665 and 1667 megahertz.
Right, so they are pretty far apart on the dial.
Exactly. In older narrowband telescopes, you would have to run a dedicated observation tuned to the redshifted HI frequency and a completely separate observation tuned to the redshifted OH frequency.
Which takes twice as long. And the conditions might change.
Right. But MeerKAT's fractional bandwidth is so wide that both of these vastly separated, heavily redshifted lines fell perfectly within a single observing window.
But why is capturing both of them at the exact same time so critical? Like, what does the combination of hydrogen absorption and hydroxyl emission tell us that we couldn't figure out from just one or the other?
It breaks the degeneracy of the galaxy's internal kinematics.
Okay, English, please.
Right, sorry. The hydroxyl megamaser is an emission line. It is adding energy to the spectrum. It tells us where the dense, highly excited molecular gas is, which usually traces the intense starburst regions or the immediate vicinity of the active galactic nucleus.
So the emission shows us where the fire is?
Exactly. The neutral hydrogen, however, was seen in absorption.
Meaning it's blocking light.
Yes. This means there's a massive cloud of cold, unexcited atomic gas sitting in front of the radio continuum source of the galaxy, absorbing the background light.
Oh, wow. So you have a cold cloud casting a shadow over the glowing core.
Spot on. And by measuring the Doppler shift of the emission line against the Doppler shift of the absorption line, astronomers can map the physical geometry of the merger.
Because they can see which parts are moving toward us and which are moving away?
Yes. They can literally see the cold gas falling inward toward the core, fueling the massive starburst that is simultaneously firing off the maser.
So it provides a three-dimensional anatomical map of a galaxy in the throes of a catastrophic collision.
That's exactly what it does.
That is just phenomenal. But wait, I have to go back to the 5-hour thing.
Right.
Because even with cryogenically cooled receivers, an 8-kilometer virtual aperture, and supercomputers running terabytes of phase referencing algorithms, the math for a 5-hour detection of a Z equals 1 megamaser still feels pushed beyond the limit.
You're right to be skeptical.
Yeah, the inverse square law is unforgiving. There had to be an environmental variable, something outside the telescope's hardware, that amplified the flux density to a detectable threshold in such a short window.
You are entirely correct. The inherent luminosity of the megamaser, combined with the extreme sensitivity of MeerKAT, would not have been enough to achieve this detection in 5 hours.
I knew it. So what happened?
The observation required a massive multiplier, and nature provided one through the mechanics of general relativity. The signal was gravitationally lensed.
Gravitational lensing. Okay, this is where we shift from quantum mechanics to the macro physics of spacetime.
We do indeed.
Because gravitational lensing fundamentally relies on mass warping the fabric of the universe, right?
Exactly. According to Einstein's general theory of relativity, mass dictates how spacetime curves, and spacetime dictates how mass and light moves.
Right.
If you have a massive object, like a massive foreground elliptical or disk galaxy sitting precisely between Earth and a distant background source,
It creates a dip.
yeah, the gravitational field of that foreground galaxy creates a deep potential well in spacetime. When the radio waves from our distant megamaser enter that well, their paths are bent.
So the light isn't traveling in a straight line anymore. It's following the geodesic, the curve of space-time created by that intervening galaxy.
Yes. And the geometric consequence of this bending is magnification. The gravitational lens takes light rays that would have normally missed Earth entirely, rays that were heading off to empty space, and bends them back toward our line of sight.
It literally acts as nature's magnifying glass.
It really does.
But how do we know for certain that it's lens? Like, how can astronomers tell the difference between a background galaxy that is just intrinsically incredibly bright and a fainter galaxy that just happens to be magnified by a foreground mass?
It leaves a distinct spatial signature. A gravitational lens doesn't just make the object brighter, it distorts its shape.
Distorts it how?
Well, depending on the exact alignment, the background source can be split into multiple distinct images. Or, if the alignment is nearly perfect, the light is smeared into a complete circle around the foreground mass.
Oh, like an Einstein ring.
Exactly, an Einstein ring. While the total flux, the amount of energy we receive, is magnified by a specific factor, denoted as μ, the surface brightness of the source is conserved.
So it just looks bigger on the sky.
Right. The lens increases the apparent solid angle of the source on the sky. The MeerKAT data, combined with multi-wavelength follow-up observations, revealed this characteristic spatial distortion.
And that magnification factor was what finally bumped the signal-to-noise ratio over the line.
High enough to bump the signal-to-noise ratio of the megamaser over the detection threshold in just 5 hours.
Which highlights a fascinating synergy in modern astrophysics. I mean, we build these incredibly sophisticated, computationally heavy interferometers on Earth, but their ultimate reach is still dictated by the chaotic, random geometry of the universe.
We are very much at the mercy of the cosmos.
We are using nature's own optics to extend the baseline of human engineering. It's poetic, almost. But I want to pivot back to the source itself, to the astrophysics of the merging galaxy.
See it at the time.
Right. We established that the hydroxyl megamaser requires a massive injection of infrared energy to pump the molecules, and that this points to a violent galaxy merger. Let's walk through the anatomy of that merger. When two galaxies collide, what is the physical sequence of events that leads to this extreme state?
Well, the term collision can sometimes be a bit misleading because galaxies are mostly empty space.
Right, it's not like two brick walls hitting each other.
Exactly. When two massive galaxies merge, the individual stars almost never collide. They just pass right by each other. Instead, the dominant forces are gravitational and hydrodynamic.
Hydrodynamic, so fluid dynamics, the gas.
Yes. As the two galaxies approach each other, their mutual gravitational pull induces massive tidal forces. These forces disrupt the ordered rotational orbits of the stars and the gas, throwing off long tidal tails of material.
So the structural integrity of the spiral arms, the disk, everything is completely shredded.
Completely. It looks like a train wreck. But the most crucial interaction happens with the interstellar medium, the massive clouds of gas and dust.
Because unlike the stars, the gas clouds actually do hit each other.
Exactly. These hydrodynamic collisions create massive shock waves that compress the gas, triggering an explosive wave of star formation across the interacting system.
Hence the massive infrared heat we talked about earlier.
Right. Furthermore, the tidal forces strip the gas of its angular momentum.
Wait, sorry to interrupt, but by angular momentum, you mean like its rotational spin around the galaxy?
Exactly, yeah. It's spin. The gas is usually orbiting nicely, but the collision scrambles that. And without angular momentum to keep it in orbit, millions of solar masses of gas suddenly plunge straight down toward the gravitational center of the merging system.
And sitting in the center of each of those original galaxies is a supermassive black hole.
Exactly. Two of them, now heading toward the same center point. The sudden influx of gas funnels directly into the central regions, creating a massive, dense, circumnuclear disk.
A giant buffet for the black holes.
A very messy buffet. This disk feeds the supermassive black holes, turning them into highly luminous active galactic nuclei. The intense radiation from these feeding black holes, combined with the extreme density of young, hot stars in the nuclear region, heats the surrounding dust cocoon.
And there it is. That's the exact environment, the dense molecular gas, the intense far-infrared radiation field required to pump the hydroxyl megamaser.
That's it. You've built the laser.
And this massive dust cocoon also explains why radio astronomy is the necessary tool here, doesn't it? If you pointed an optical telescope like Hubble or Webb, well, Webb is infrared, but if you used an optical telescope on this merging system, you wouldn't see the black holes, right?
You wouldn't even see the peak of the starburst in optical light. You would just see a dark, obscuring smear of dust.
Because the optical light, the ultraviolet light from the young stars, is completely absorbed and scattered by the dust grains.
That is the principle of dust extinction. Optical wavelengths are similar in size to the dust grains themselves, so they interact strongly and get absorbed or scattered.
Like trying to drive through a thick fog with your high beams on, the light just reflects back at you.
Great analogy. But radio waves, operating at wavelengths of centimeters or meters, are vastly larger than the dust grains. They pass through the obscuring torus completely unimpeded.
So the megamaser is a beacon punching directly through the dust.
It allows us to probe the gas kinematics within the central parsecs of the merger, right where the action is.
And what's happening in those central parsecs is arguably the most extreme physics in the universe. We have two supermassive black holes, each potentially billions of times the mass of our sun, that have been dragged to the center of this newly formed megagalaxy.
It's an unimaginable amount of mass.
What happens to them next? They don't just immediately fuse together, do they?
No, they don't. They undergo a complex orbital evolution driven by something called dynamical friction.
Dynamical friction? How does friction work in space?
As the two supermassive black holes move through the dense background of stars and gas in the core, their immense gravity pulls a wake of material behind them.
Like a boat moving through water.
Yes. And this wake of material exerts a backward gravitational pull on the black holes, slowly sapping their orbital energy.
Oh, I see. So it acts as a drag force.
Exactly. Because of this drag, they begin to spiral inward, forming a binary supermassive black hole system.
This is what we refer to as the final parsec problem in astrophysics, right?
Yes, it is.
The idea that dynamical friction works really well at large distances to bring the black holes close together, but as their orbit shrinks, they eventually scatter all the nearby stars out of the core like a gravitational slingshot.
Right, they clear out their own neighborhood.
And once the stars are gone, the friction stops. So technically, shouldn't the black holes just orbit each other forever, separated by about a parsec, unable to close that final distance?
That was a significant theoretical hurdle for many years. Theorists couldn't figure out how to get them to actually merge. However, systems like our hydroxyl megamaser provide the solution.
The gas.
The massive influx of gas we discussed, the exact same gas feeding the maser, provides the necessary drag. The black holes embed themselves in a massive, viscous gas disk.
So even if the stars are gone, the gas is still there dragging them down.
Exactly. The torque from this gas disk continues to drain their angular momentum, allowing them to cross that final parsec.
And as they spiral closer and closer, they enter the final stage of their evolution, the point where the orbital velocities reach a significant fraction of the speed of light.
Yes. And that's when things get truly relativistic.
They begin to emit gravitational waves.
The sheer mass and acceleration of the binary system warp space-time so severely that they radiate their orbital energy away in the form of low-frequency nanohertz gravitational waves.
So the megamaser is effectively the precursor signal.
It highlights the dense, gas-rich environment that guarantees these black holes will eventually merge. And when they do, they will release a cataclysmic burst of gravitational wave energy that will ripple across the entire universe.
So catching the Z=1 megamaser isn't just about finding a distant molecule. It is about actively mapping the evolutionary pipeline of supermassive black hole mergers at the peak of cosmic activity.
That's the real science here.
And because MeerKAT proved this can be done rapidly in just 5 hours with the aid of a lens, it really forces a paradigm shift in how we approach observational astronomy going forward.
It absolutely does.
We are no longer limited to targeted, deeply integrated observations of single objects over hundreds of hours. We are moving into the era of massive synoptic surveys.
That is the true legacy of this detection. MeerKAT is a pathfinder. It is a precursor facility for the Square Kilometre Array, or SKA,
which will be the largest and most sensitive radio observatory ever constructed.
by a wide margin. The SKA mid-array will be built in South Africa, integrating the existing MeerKAT dishes and adding hundreds more.
Hundreds more. That is going to be a massive footprint.
And meanwhile, the next generation, very large array, the NGVLA, is being developed in the U.S. to cover higher frequency ranges.
The leap in sensitivity and baseline coverage with the SKA will be exponential. I mean, if MeerKAT can pull a lensed megamaser out of the noise in 5 hours, what does the data stream look like when the SKA comes online?
Honestly, the data rate will scale from terabytes to petabytes.
Petabytes, that's 1,000,000 gigabytes.
The processing requirements will be so immense that the data cannot be recorded and analyzed later. It physically can't be stored. It must be processed in real time by dedicated supercomputing clusters distributed globally.
So the car wash has to run while the car is driving at 1,000 miles an hour.
That's one way to put it. The algorithms we discussed, the RFI mitigation, the phase referencing, the cross-correlation, they will rely heavily on machine learning to automate the extraction of signals.
Human eyes won't even be able to look at all the data.
Never. The SKA will not just find one or two of these high redshift megamasers. It will conduct blind surveys of the sky, potentially detecting hundreds or thousands of them.
It will effectively create a statistical map of cosmic violence. We will be able to trace the exact merger rate of galaxies, the evolution of gas fractions, and the buildup of supermassive black holes across the entire history of the universe.
Which writes the missing chapters of our cosmic history.
And the fact that South Africa is driving this, not just hosting the hardware, but developing the computational infrastructure at IDEA and leading the data analysis, it really cements the shift toward a decentralized global approach to massive data-intensive astronomy.
It is a critical development for the global scientific community. The bottleneck in modern astronomy is no longer photon collection. We know how to build big dishes.
Right.
The bottleneck is data processing and algorithmic efficiency. The expertise developed to scrub the MeerKAT data and extract this hyperfaint hydroxyl line is exactly the expertise required to operate the next generation of global megascience projects.
So we are fundamentally changing our relationship with the universe, moving from an era of taking static pictures to an era of continuously monitoring the dynamic structural evolution of space-time itself.
Exactly. It's astronomy in high-definition video instead of Polaroids.
We have covered immense ground today.
We really have.
We've explored how the metric expansion of the universe stretches the frequency of an 8-billion-year-old signal, allowing us to peer into the gas-rich, violent environments of the cosmic dawn. We've decoded the quantum mechanics of the hydroxyl radical.
Hyperfine structure.
Right. Understanding how far infrared radiation pumps the molecules into a population inversion, setting the stage for a cascading wave of stimulated microwave emission. We looked at the engineering marvel of MeerKAT, how it uses aperture synthesis and algorithmic phase referencing to isolate a hyperfaint signal from a deluge of terrestrial noise.
All while capturing both neutral hydrogen absorption and hydroxyl emissions simultaneously.
Yes. And we saw how the mass of a foreground galaxy warped spacetime to act as a gravitational lens, boosting the flux density to a detectable level. Finally, we broke down the astrophysics of the merger itself, how dynamical friction and massive gas inflows strip angular momentum, feeding the supermassive black holes and driving them toward an eventual space-time shattering collision.
That sums it up perfectly.
But there is one final, profound implication of all this that ties the deep past directly to our immediate present.
Oh.
Yeah, we established that the universe at z=1 was dominated by these violent mergers, and that the supermassive black holes at the centers of these merging galaxies inevitably spiral inward, emitting nanohertz gravitational waves.
Right, the precursor signal.
So think about this. If the early universe was literally filled with countless galaxy collisions just like the one that fired this megamaser, the gravitational waves from those billions of mergers didn't just disappear.
No, they didn't. They propagated outward.
Overlapping and interfering with each other across billions of years. It means that the very fabric of the space-time you are sitting in right now is subtly, constantly vibrating with the ancient, unseen echoes of billions of cosmic wars.
A stochastic gravitational wave background.
Exactly. A background hum of cosmic violence that we are only just now beginning to detect. It is a sobering reminder that the violent history of the universe isn't just something we observe through a telescope. It is the physical foundation of the reality we inhabit. Something to think about the next time you look up at a quiet night sky.